are a part of this GAN course on thermochemical conversion of biomass waste to bioenergy and value-added products. So we are starting our third day of session today. As promised, Professor Ang will be discussing more on microalgal biofuel production, that is 3G biofuel production in today's session. So without delay, let me welcome Professor Ang for this session. And Professor Ang, the floor is yours.
One. So welcome back to the third day of our GAN course about the thermochemical conversion about the biomass. So today the topic that I would like to discuss is about the microalgae biomass. So how we are going to turn the microalgae biomass waste into the biochar or maybe bioenergy or bio products. So today I will start from more fundamentals. I would like to introduce you about what is the biochar. So actually the biochar is one of the solid products will be produced during the thermochemical process. I mean the solid product. So for any thermochemical production process, three types of the product will be produced. First is the liquid product, the solid product, and also the vapor or gas product. So for the last 2 days, I focused more on the liquid product from the biomass waste or biomass into the liquid product. So today I will focus more on the solid product. One type of the solid product I will produce is the biochar. So whatever name that you want to name it, the hydrochar, maybe with a relatively lower temperature, higher temperature, which I call it the solid product. So the end product, maybe we can call it the biochar. So what is the biochar? So biochar is one of the products that rich in the carbons, the carbon content, from the biomass heat under the unlimited of the oxygen. This is the keyword. Limited. Limited of the oxygen. If with the oxygen, what will happen? Combustion. Combustion, it will become ash. Ash. No longer the biochar product. So that's why this is very important. Throughout the thermochemical process, if you want to get the biochar or the solid product, that useful solid product must be under the limited oxygen or even no oxygen. Limited because sometimes the condition is very difficult with no oxygen, because in our air have more than 20% of the oxygen. So sometimes it's very hard to limit it to the total no oxygen. So that's why I said limited oxygen. If possible, make it no oxygen. No oxygen. So if without any oxygen, so no any combustion might be happen. So your biochar product might be better. So it can be made by the thermochemical conversion, as I mentioned. Throughout the thermochemical conversion, there are many different types of the thermochemical conversion, which I will discuss later. So what is the main purpose of the biochar or the solid product, the end product? So firstly, if the biochar without any further, or what I mean is without any further treatment, we can use as the bio energy directly, or can be used as the carbon sequestration directly, because why? This is the carbon-rich material. Can reduce the carbon, can store the carbon. Can be used as the bioabsorbent directly, bioabsorbent. So you can put the bacteria inside the biochar. So it can be the housings for your bacteria or your fertilizer. So can be used as soil fertilizer. For the soil fertilizer is suitable to be used as house for the soil fertilizer. Can be used as the bio fertilizer, and also for the bioabsorbent can absorb some pollutant methods. So this is about the biochar. Then today the biomass that we would like to discuss is about the microalgae. So like Dr. Namia already mentioned, the microalgae is the third generation of the feedstock for biofuel and bioenergy. It's the third generation, because previously the last 2 days I've been discussing about the non-edible feedstock. For the non-edible feedstock, we got the second generation. Of course, the first generation is what? Yes, correct. Yeah, it's a edible feedstock which currently market are using still the first generation. Mainly focusing on I can say the more than 85% are still using the first generation. So we need to explore what is the potential of the third generation. We even have the fourth generation. Have you heard about the fourth generation? What is that? The fourth generation. Genetic modified microalgae. Yeah. Yep. Then for the microalgae, I guess most of you know what is the microalgae because it has the high photosynthesis ability and also the growth rate. It can be matured from the very beginning for the cultivation process until it matured is less than 1 month. Or normally it's just take if for the Chlorella species, it depends on species. If for the Chlorella species, it take maybe just 2 weeks, 15 days. Until it's a maximum or the optimum productivity, just 15 days, 15 days. And also, it has a very high photosynthesis. Why the photosynthesis? Photosynthesis means it only consumes what? Photo, sunlight. Photo is what? Sun. Correct not? Photo is sun, sunlight, and CO2. So during the cultivation of the microalgae is totally net zero emission, I can say, because it's used the what? Sunlight and also the CO2. It consumes the CO2 for the growth rate. So what is the main components for the microalgae? It has the lipid, protein, and carbohydrate. Of course, it has other component. So this is the main component consists in the microalgae. The lipid content, the protein, and also the carbohydrates. So how? This is the pathway. This is briefly introduced about the pathway from the cultivation of the microalgae up to the microalgae-based products. First is the cultivation. After the cultivation until it's matured, it takes about 2 weeks for the Chlorella species. Then after that we can harvest it. Then rewater of the microalgae. Then sometimes you can see the powder of the microalgae right now. Then normally people culture the microalgae for what? For the pharmaceutical applications to extract the useful compound from the microalgae for your supplement. Right now, supplement. So after that, the waste microalgae, what you going to do? And this one what we can do it. And now to convert it into the some useful products. Then we can do the extraction, extract whatever that you want, and purifying. And after that, we have the microalgae based products for the pharmaceutical products. This and also the supplement. This is the main two products that currently the cultivation of the microalgae, the main purpose. Then after that, we also can be used as a biofuel because why? The microalgae has very very rich in the lipid content. The lipid content can be converted into what? Biofuel or biodiesel. And also the carbohydrate also. Carbohydrate is one type of the can be converted and degraded into the what? Sugar. Using sugar then can be converted into the bioethanol as well. So it can be used as a biofuel. Then the biomass waste can be also used as a animal feed. After it drying, can be used as animal feed. That one. So this is a brief introduction about the microalgae. So yeah, when we talk about the thermochemical conversion now, the main product is what the feedstock is microalgae, but it can be used in any type of the biomass. You see. For the I divided into the 3 categories. One is the reaction environment. Reaction environment that means whether it has the air or not. Air I mean the oxygen, with the oxygen or without the oxygen. So you see, if with the oxygen, like all of you already know, the combustion or core firing what will happen. If the combustion happen, it means what? Heat and or steam will be produced. So throughout the combustion process, thermochemical combustion process, so we can generate what? The energy. Of course, you can generate the energy. Energy in the form of what? Heat and steam. then can what? Run your generator to produce the electricity, the steam turbine to generate the electricity directly throughout the generator, correct not? So this one through the combustion, thermal chemicals are under the with the oxygen or the air. It's the combustion process that can produce the heat or steam. Then after that, heat or steam, then we go through what? Your generator to produce electricity directly or another sort of energy directly. So the energy is keep transforming. Then with the limited air, why the gasification is a limited air? Because you see, the main product for the gasification is what? Biosyn gas. Biosyn gas. We need some air. For what? To produce the syngas. To produce the syngas. Sometimes we need the first in into the air, steam air, gas steam air to what? To get more hydrogen. The more hydrogen, so that we can produce the biohydrogen throughout the gasification process. So that's why with the restricted or limited air, we can throughout the gasification we can get the syngas. Of course, the heat will be generated as well throughout the gasification process. So this is the two main products. Then the thermochemical process that we all know is what? The pyrolysis, the torrefaction or liquefaction. These three processes we keep discussing for the past 2 days, right now. That one is with totally no air. With no air. You see, for the torrefaction, which is the, I can say is a mild pyrolysis, which the main product is what? The biochar. So this study we are using the torrefaction to get the biochar. Biochar is the main product. Of course, the byproduct will produce the liquid products and also the gas products little bit. Gas is really little bit because it is below temperatures. So the main product is the biochar. The liquefaction, we can get both biogas and bio oil or biochar, or you call it the hydrochar, for the liquefaction, or the hydrothermal, we call it the hydrothermal carbonization, whatever name that you want to call. Because why? What is the product that you want to focus, and you name it the process that the name. So actually the concept is the same. It's a liquefaction. That means you go through the thermal process with the vapor form or the liquid form. That one we call the liquefaction or the hydrothermal with the water hydrothermal. For the hydrothermal, the main product is the what? The hydrochar. You want to get hydrochar, then some of you want to get the bio oil. Then a little bit of the what? Gas, syngas will be produced. The last one is the pyrolysis process, which most of the industry currently using the pyrolysis process to degrade the thing. So degrade the biomass. So the main product can be bio oil or biochar. Can be it depends on the conditions that you want to focus on. Can be bio oil or biochar. Then the both will be produced as well. Then of course the biogas. Good amount of the biogas will be produced. So from the industry project, I already discussed last few days. The biogas that produced normally we feed back into the burner or the turbine, or the turbine for the pyrolysis process, because normally the pyrolysis process run at around 500 degrees C. For the optimum, the minimum temperature to optimize the bio oil or the biochar is around 500 degrees C. So in order to run up to that temperature and maintain that temperature, the electricity that input is relatively high. If we just rely on the electricity, the overall production cost might be very, very high. So that's why normally we will feed back the syngas that produced through the pyrolysis process, because pyrolysis process is produce a rich amount of the syngas, or biosyngas, we call biosyngas. So that's why can feed back to the pyrolysis reactors. to run the pyrolysis process and to get your bio oil product or the biochar product. So for the pyrolysis process, three products that we produce. The amount roughly the amount of the three products is range between 30 to 40%. It depends on your condition and your focus. 30 to 40%. Sometimes maybe 35% of the bio oil, 35% of the biochar, and another 30% is your biogas. Sometimes if you want to set the conditions to produce more defined biochar, maybe the biochar process biochar yield can be reached up to 40% or 45%, because if your product is the biochar, you want to focus on biochar, then the bio oil relatively maybe small. Then some amount, a little bit amount of the biogas. It really depends on the condition and also the raw material that you are focusing. So in this study, particular this study, we are using what? We are using the total fractions, total fractions. So total fractions, they still divided into the two types of the total fractions. One is the dry total fractions, another one is the wet total fraction. Wet total fraction we can call it the hydrothermal total fraction. Hydrothermal, same with your liquid fraction process. This one is a relatively low temperature, that's why we call it the hydrothermal total fraction. So for those still don't know what is the total fraction, is relatively mild pyrolysis. That's why I keep mentioning this mild pyrolysis with a relatively low temperature, which happening around 200 to 300 degrees C. For the reaction time around 15 to 16 minutes, depend on the product that you are focusing. With the total fraction, we are able to enhance the calorific value and energy content, as well as the carbon content of your product. What is the product? Still remember what is the product for production? Biochar. Yeah, able to enhance the calorific value for the biochar. Because for this study, our main aim is what? To produce the biochar that can be used as a solid fuel. Solid fuel. As a solid fuel. Then it's able to reduce the moisture content throughout the process. So without to reduce the moisture content. So biochar is the main product. While for the wet production, we can use the water as the reactive medium for the subcritical water that we keep in the liquid phase, but below the critical temperature of the water, because 374 degrees C, at around 150 to 240 degrees C, with more than 5 bar, because with the water as a medium, one will heat up more than 100 degrees C. The temperature, the pressure will be increased as well. The temperature increase, the pressure will be increased. So normally, it happens more than 5 bar to 10 bar. If you run at 160 degrees C, easily can up to 10 bar. So it is an attractive method to convert the wet biomass into the biochar without the drying process. Because this one the drying process, because the microalgae normally are in the wet form. So we don't want to waste the energy for the drying process. So that's why. Or we can dry under the sunlight, but it takes few days. Then we choose this process and we see what is the feasibility of this process. Yeah, problem statement. So in order for you to conduct the one research, this one is academic research, you need to figure out what your problem statement, what you want to solve. What is the problem that you want to solve? So high demand of the non-renewable energy has created the energy crisis. This one is a general form, but microalgae biomass has a relatively low carbon content. Because we want to convert into the the solid product. No carbon content, low energy content, and low calorific value is not suitable to be used as a fuel. The hydrocarbon, not because the fuel. What is the fuel? Fuel content of what? C and H, hydrocarbon. So low calorific value. So the high moisture because high moisture, you know, because microalgae concentrated in the water require for the non-renewable energy to dry before the thermochemical process. It goes through the thermochemical process and the dry process. Thermochemical process that we mentioned here is like the pyrolysis. Normally we are using the pyrolysis or even the gasification. Gasification also need to be dry. So bio oil produced from the microalgae pyrolysis has with a disadvantage, including the low chemical and thermal stability with the high oxygen and water content, has very strong acidic which limit energy application and development. So because from the previous study we found that for the biomass, the microalgae biomass, after the extraction, the waste, then we want to try to convert or extract the bio oil. It's very difficult and the quality of the bio is not very good. So this one, I think yesterday or the day before, we mentioned about the microalgae. Microalgae, yes, the microalgae have the highest yield per land area, per hectares, per land area. But during the extraction, it's very difficult. The amount of the extraction is maybe just around 10%, I can say. 10% of the microalgae, the weight of the microalgae. For example, you have 1 kg, you only can extract out how many? 100, 1 ml, this one is an ml, not liters. Then, in order for you to get 1 kg of the microalgae, you need to have 1 kg, how many? I don't know how many liters already. Normally it's 10 grams per liter, you know. 10 grams per liter of the water. It's a very good 10. So that's why. But in overall, the yield still highest. Then the microalgae gets contamination easily if we have the large scale cultivations, open pond large scale cultivation. Okay. Then the reactor design and scale up for the pyrolysis require the appropriate kinetic study to understand about the biomass. This one. In this study, we also embedded some kinetics studies to understand what is the biomass reaction. So to see what is the suitable temperature for the hydrothermal process. So in this study, we have 3 objectives. First thing, we still investigate the dry convection. We need to compare because we know that the dry convection will produce the good product because it's totally dry. Correct not? Then we have to compare with the advanced wet convection. Okay, why I add the one, the word one here? We are using the microwave. This one is a microwave. We are using the microwave. So we compare these two process. What is the difference between these two process? Compare with the same feedstock. Why I compare the Jatopa biomass? This one, the Jatopa biomass is what? You still remember, I'm doing the research about the Jatopa oil. Then this one is the Jatopa, the oil biomass. The leftover biomass. So we want to see what is the effect. And after that, to analyze the effect of the tolerance on the microalgae using the advanced TGF-TRL, PY, GCNS. That one is what? We want to see. We want to see in detail what is the effect of the toleration. For example, the TG. The TG is we install the TGA before the FTIR to what? To heat up the microalgae to the desired temperature. Desired temperature is what our tolerance function temperature. So that it's go through the simulated pyrolysis process. Then at the same time, we see what is the product we can get. At which temperature, what type of product will we produce. Then so that when we want to conduct the toleration, we know what is the temperature that we can heat it up so that we can have the certain targeted product. That's the thing. Similarly, for the PY GCMS also same. We want to see what is the product. So for the PY GCMS, we even conduct double shot. Double shot, means what? Double shot, means 2 times of the pyrolysis. 2 times of pyrolysis is what? The first time is the pre-treatment of the lower temperature, which is the torrefaction, then followed by the what? Followed by the pyrolysis. See what is the product. So compare with without the pyrolysis. No, without the torrefaction process. So what is the product that we change? Later on you will see the result. It's different. After the torrefaction, the product that you get might be different. So lastly, we want to see the effect of the wet convection on the pyrolysis kinetics using the microalgae. Of microalgae, using the independent parallel reference. This one is a kinetic study. So this one is the methodology for objective respectively. These are objective 1, 2, 3, 4. This one is the dry convection, like usual. In this study, we are using two types of the microalgae, which is the Chlorella ESP31. ESP31, what you need to know, you don't need to know the scientific name. ESP31 is, you need to know is what? High in carbohydrates. And another one is the FSP, is high in protein. This one you need to know. Because this one will affect our result. So high in carbohydrates, then what is the outcome? Then high in the protein, what is the outcome? Why we have the Chlorella or the microalgae high with the protein? Because as I mentioned, the industry want to culture the algae to extract the protein. To extract the protein. So that's why we want to see what is the effect. Of course, we compare with the total biomass. See what is the effect. With the torrefaction temperature between 200 to 300 degrees C for 15 to 16 minutes. Then we analyze the fuel properties, analyze the characteristics, and also the torrefaction severity index. This is the dry torrefaction. Then compare with the wet torrefaction. Wet torrefaction, we are using the microwave reactor. We are using the microwave reactor. Then with the acid solution, we use the organic and also the inorganic acids because we want the acid hydrolysis to take place. So after we put in the acid and without the acid, the pathway reaction pathway is different. And conduct at the wet torrefaction at 160 degrees C and 6 bar. And similarly, we analyze the fuel properties, the chemical, physiochemical properties, and also the hydrolysis composition of the product. This is then after that we compare between the dry and also the wet torrefaction. What is the difference? After that, we also study in-depth analysis. In-depth analysis, just now I mentioned, we want to see what is the effect of the temperature towards the product, the microalgae biomass product. So that's why we have the real-time gas analysis. Real-time means what? We heat it up. At the same time, the product, the gas keep sending to the FDR to capture what is the product, the real-time product. Similarly, we have the single and double shot of the analysis. Then go through the GCN gas. GCN. Single shot is what? Single shot is directly to the pyrolysis. Or double shot is up torrefaction, then pyrolysis. Then see what is the difference. What is the product difference. Then we can see what is the product distribution of the protein, carbohydrate, and lipid. The protein, the carbohydrate will produce what? The protein will produce what? And also the lipid will go back. Yeah, this is what we study. Then after that is we study the kinetic study, the kinetic model. The main purpose for the kinetic model is we want to see the activation energy. What is the activation energy for the product, for the sample?
What was the moisture content in the original moisture content?
Later I will show you what is the later I think later will show you. So this is the initial property, so that's why I mentioned when you want to analyze the certain samples, you need to know what is the composition, what is the possible analysis, and also the element analysis. So this is the two types of the microalgae. You don't need to know the scientific name. You just need to know is the correct the ESP31 rich in carbohydrate. For the carbohydrate, this is your correct the CV. Then another one is this is a modified microalgae. Microalgae still correct but it's modified. Name is as the FSPE. This one is rich in protein. Because the pharmaceutical company they want to extract the protein. This one is rich in protein. So this is the HHV and also the hydrogen to carbon atomic ratio. This one we done it on the element analysis to see what is the CH, N and O. CH, N and O. And to calculate the ratio. This is the microwave analysis. As I mentioned that day, we modify the household microwave and design this reactor to control the pressure and also the temperature, and put in the nitrogen gas so that it's free from what oxygen. Two biomass samples with just one condition, but in this study we study the different liquid mediums, which is using the acid, water, sulfuric acid, and phosphoric acid. Phosphoric acid with the different acid concentrations. So this is a microwave conversion. This one is what? To analyze the microalgae potential composition. Because this one is a raw and wet purified microalgae. This one go through the wet convection. Then after that, these two studies. One is the TGA, TGA. After the TGA, then it go through the FDR directly. Then we can know what is the peak to get what is the potential product, the potential product, TG. Then this one is the what? Single and the double shot of the pyrolysis. Then connect to the what? To the GCMS directly. This one we heat it up here. The pyrolysis to simulate.
So in the FTIR plot, what is the two axes that are there in these?
Sorry?
FTIR plot.
FTIR, yes.
What are the two x-axes that we have? So one would be the intensity of peak generated, and what are the two axes that we have?
This one we convert in two axes to see what is the peak. Yeah.
What is on the x and the y?
What is exactly the difference between x and y?
What are we measuring?
What are we measuring? Y would be the intensity of peak that's generated, right?
You see FTIR, we only can see the bond. What's the bond only? The bond, I mean the carbon, for example, the carbon to O, C and O, the peak is the C and O.
Okay, H upon C and O.
Functional group only. We only can know the functional group, then we get what is that. Then compare to the standards. Yeah. Yes.
I have a question.
Yes.
In the slide number 14, just previous slide.
Slide number 14, yes.
Yeah. In this schematic diagram, you have shown that there is a pressure gauge.
Yes, correct.
Attached to the back pressure valve.
Yeah.
So, in how much pressure do you operate this wet microwave assisted wet polymer?
No. Okay, this one because this one is not the pressure reactor. Not the pressure reactor. That means what? We cannot control both pressure and temperature. Either you control the temperature, the pressure will follow. The pressure we just measure the pressure. What the pressure? We didn't control the pressure. Either you want to control the pressure, then measure back the temperature. That's it. Because this is not the pressure reactor. If the pressure reactor is very expensive, and you can control both pressure and temperature as you want. Yeah. This one is not. This one is just to avoid that the pressure of the reactor up to the certain limit, then it will release the pressure. That's it. We are not controlling the pressure for this reactor.
So this is just to release the pressure.
Release the pressure in case of the pressure up to the certain pressure, certain critical pressure. For this, if not mistaken, for this reactor, the maximum pressure that can take is 20 bar only. 20 bar. If it reach up to 20 bar, it can release. You understand? So what is not control the pressure. Yes, in this reactor, we can control the pressure, but after we control pressure, you cannot control the temperature. Temperature and pressure you only can control because they are the correlation. You understand? Because with the liquid samples. With the liquid samples.
It's not a high pressure reactor, right?
Cannot high pressure, not high pressure. This is not the high pressure reactor.
PRV is say 20 PRV. Pressure releasing valve. So that is set at 20.
20, yes. Correct, 20. Just to read the pressure. Then for our this experiment, so that's why we cannot heat it at a too high temperature. If more than 200 degrees C, the pressure definitely more than 20 bar. More than 20 bar. So that's why we run at 160, 170 only. Because our reactor cannot take the high pressure. And cannot control. No, can control the pressure. Either we can control pressure or temperature. That's all. Cannot control both. Yeah.
So what is the flow rate of nitrogen?
Flow rate. This one. The flow rate is not important because we pump in the nitrogen. Then after that we let it react because this is a closed system. We pump in the hydrogen until there are no any oxygen. We put it until a certain time. Then we push up the oxygen. And we off it. Not continuous. This is not this is the batch reactor. Yeah, batch reactor. Not continuing not continuing reactor. This is a batch reactor. One batch reactor. Yeah.
Sir, what is the function of acid here? Why do we add acid? Is it for increasing the digestion rate?
Function. I did tell you because the function is what we want. The hydrolysis happen. Hydrolysis took place during the reaction. During the reaction, we want the hydrolysis took place, which the acids can these all acids can provide you with the H plus. Yeah, acidic. So that the acid hydrolysis took place. Yeah.
Biomass is already very good. So we need to dry it and add acid along with water.
No. We fix at a certain amount of the liquid amount. For example, this one I can't remember how many percent already. Maybe if not mistaken 50%. For example, the dry biomass is 50% and the liquid sample is 50%. And also the acid I can't remember how many the amount already. But what we want is the acid hydrolysis took place at the same time, so that it can modify the biochar that you produce, so that it can increase the porosity of the biochar.
How is it increased? By X plus the porosity?
Because the acid hydrolysis will took place, so that the reaction later I will show you. Wait a minute, I think I show you here or not. This is the pathway. So this is the pathway. That means you see, if we put the acid hydrolysis, the glucose will produce. Glucose produced, then we have the 5-HM. This is 5-HM is another chemical product. Chemical product that you put in the industry. This one is another. So that's why I put in the H plus. The pathway is totally different without the hydrolysis. This one thing. Second thing, the biochar. The biochar will be in a different properties under the SEM. So this is a pathway. So it is a pathway based on our result. This one. Then we believe. This one we don't know. We just believe. oh, this one, the carbohydrate, will change to the sugars, we have the furans and also the ketone. This one we believe from this all analysis. Yeah, we believe this one will come up. This is the pathway that we are following. So that's why before that I keep mentioning you need to design your process so that the process can push towards the reaction that you want. You know, one process, so many reactions will be happen. We don't know which one is happen. We don't know which one happen. But through the further analysis, maybe we can get, oh, maybe this one, maybe this one. Why? Because through the FPR, we know the functional group 8. That is the potential product. That potential product, maybe it's the furans, for example. Maybe this one is the has the aromatic compound, for example. Because we see the functional group 8, this one is from the aromatic compound. Maybe it's already follow that pathway, for example. Yeah. So that's why we need to design. So the lipid maybe is converted into the fatty acid, but for the lipid is quite direct because lipid normally if you are go to the fatty acid, that one is quite direct. That one. So it goes through the cracking process. Yeah. So this is the pathway. So we have the secondary cracking also. This. Yeah. So for so how we going to know? So through this one, the detailed analysis, because from just the normal hydrothermal process, this is the industrial process. Hydrothermal process, we don't know what is the pathway. We only can see what is the end product, but what is happened in between, we don't know. We don't know. So that's why throughout this analysis, further analysis, then we can know, we can guess. Oh, what is that? You can read it up. Yep. That's the thing. So anything. You see this one. For the we do the two state of the thermal degradation. First shot is about 200, 250, and 300. Why? Because this one we want to do the pre-treatment, torrefaction. Then followed by the second shot is the what? Pyrolysis. Then see what is the process. Yeah. Pyrolysis. Then see what is the difference. First shot and the second shot. Yeah.
After first shot also, like, are we doing the complete analysis of the product?
Correct. After the first shot, complete analysis. Then after the second shot, complete analysis. This one is no. Yes. In this study, first shot we do the analysis. After the first shot, what happened? Then the second shot, what happened? Then without the first shot, let me directly go to pyrolysis. What will happen? So that we can compare. What is the effect of the torrefaction? What is the effect of the torrefaction? Yeah. So that's why. So some of you asking me, whether what is the pre-treatment process? What is the process before that we want to do conduct before we go to the our product? So we need to see what is the pathway. So this analysis is very important, so that we know. If you want to do the hydrothermal analysis, not hydrothermal, sorry, thermal chemicals analysis. Yes.
So when we do the single shot pyrolysis and later single shot, double shot pyrolysis, the final product is nearly similar or are the characteristics different?
Different. I can say it's different, totally different. Okay, one thing different. Very simple. After you do the first shot, the water will be removed, correct or not? The water, because water 100 after 100%, the water will be removed. Then some other compound will be removed, so that the activated energy for the second shot might be much more lower. So that's why sometimes first shot is very important. It depends. You not necessarily do shot. It depends on the product, the sample, and also the product. See what you want. Sometimes it's not necessary to be that precise. If you get your desired sample, desired product already. Not necessarily, Sometimes not necessarily. You can directly do the price. Hey, the bio oil that I get, this is what I want. No need to do anything. No need to first shot or second shot. But we are doing the scientific research. We want to know what happened, what is the potential is happening. And we do this study. Yeah, that's the thing. Or sometimes so that we can design more precise pathway towards certain products. Towards certain products. Then we can explain to people, oh, this one happened. What happened during the thermochemical process? Yeah. Besides the degradation. So normally, for the thermochemical process, even though you didn't do in this detailed analysis, what you need to do is you using do the TGA. TGA. You do the TGA, we can know what is the thermal degradation temperature for the certain product brand up. Thermal degradation, whether it contains high moisture or it contains high cellulose content or the high cellulose content. So what is the degradation temperature for that compound? Because from the TGA we can know. So normally we are conduct the TGA. Then from the TGA, we also can figure out if TGA you heat up to 900 degrees C. You also can know what is the possible analysis. Right now, possible you can know the moisture, the ash content, and the volatile matter. What is the percent of the volatile matter? Right now, yeah, that is the alternative way in order for us to analyze the possible analysis. Then after that, it is good you go through the element analysis to know what is the C, H, and N. Sometimes sulfur, if any. If not enough, CSN is enough. Oxygen is the result of C, the balance is oxygen. Plus the N. Yeah, that one is the element analysis. Analysis. Sometimes we didn't measure the H. Why? Sulfur is
For biodiesel it matters. For biochar it doesn't matter.
No, because for the normally for the sulfur is relatively low. Relatively low. This can be ignored sometimes because. And one more thing is most of the element analysis don't have the sulfur because it don't have the sulfur. Then this is the three important elements. And of course the balance is oxygen. Yeah, the balance is oxygen after considering the N. Yeah. That's how we analyze the element analysis. Then before we go to any thermochemical conversions. Yeah. So any questions so far?
This TGFK would be a simulation for dry torrefaction, right, sir, or it can be a simulation for wet torrefaction?
Oh, this one we use the raw and also the wet torrefied microalgae. We use both.
And there was another product by the name FSP or something, right? High protein, high carbohydrate, high protein content.
Oh, this one. I think this one we conduct one only. Okay, why conduct one only? Okay, because I didn't go until result yet. You don't know. You see, initially you ask one. Initially, we test on 3 samples. Correct not? 3 samples, including the topa. 3 samples. Correct not? 3 samples. So after that, we found that we didn't the jatopa we didn't further analyze in the second batch parameter. Why? Because they found that after we conduct the wet dry fermentation on the jatopa, they are not much effect. So no use to do the treatment or the dry fermentation on the jatopa. So that's why we didn't continue with jatopa in the wet fermentation because they have no effect. If no effect, I believe if we conduct the wet fermentation also will no any effect. So we didn't continue with the jatopa. Then after that, we conduct the wet fermentation. We found that the high in the protein microalgae have less impact as well because our product is a biochar. So less impact. So yes, less impact. I mean the degradation will not take place because the protein will not degrade at relatively low temperature because this one is just conduct at 160 degrees C. No effect at that low temperature. So cannot
break down that easily.
Yes, that's why I didn't continue to do further analysis. Yeah, there's no effect. No effect mean doesn't mean that no any reaction. Less reaction. This is not what we want. Less reaction. They have some reaction. They have some degradation as well. Yeah. Yep. Okay. So that's why until the third one only one sample. One sample which is the EST 31. high in the carbohydrate content. Yeah. Okay, this one is the first one, the dry convection. This one is a very common tube furnace. This one very common. I think most of you know. Tube furnace with the pump in it with the nitrogen gas. We control the flow rate using the 3 sample, which is the 2 microalgae and 1 jatopa. Then go through the gas. This one goes through the gas washings. This one, this one we conducted in 2018. The reactor we already upgrade. We already installed the condenser. Condenser system, 2 state of the condenser system. Then we can correct the bio oil. Can correct the bio oil. In this project, we just focusing on the solid product. Yeah. So this one is just the terminology, the tolerance performance. Later on, discuss what is the solid year, what is the HSP. So this is the HSP improvement and also the energy yield. So this is the raw data, not necessarily to know. So we just know that if the temperature increase, the solid yield will be decreased. Then with the increase of the holding time, increase with the holding time, the solid yield will also decrease. So what is the summary from that one? So both, of course, all the jatopa or the both microalgae will be converted into biochar. Biochar, yeah, we convert, sometimes you want to convert into the biochar, we convert, but the product is good or not, it got effect or not, we don't know. That's the thing, can be convert, of course, you conduct any experiment can be convert, can be because it's transformed already, throughout the process, it could go through some process, but the product will be improved or not improved, we don't know. We don't know. But after the further analysis, we found that what dry process has less impact on the FSP, the high protein one, and also the jatopa. Jatopa, why? Due to the lignin surrounding lignin contents, due to the different chemical composition, different things, the protein and also the lignin cannot degrade. That's why. But can be converted into the biochar? Not can. But if you want to if for the microalgae ESP, the HSP, the heating value will be increased 45%. Then the energy yield can reach up to 80%. Can be achieved with the tolerance fraction of the at 300 degrees C at 60 minutes for the HSP. So the result you can download that paper. Then while for the wet tolerance fraction, you see wet tolerance fraction. This is the solid year. For this one, we using the water and also 3 types of the acids. You see, with the adding the acid, the biochar or the sample, not to say the microalgae are further degraded, so that the total solid yield will be reduced. Mean is further degradation will happen. But you see, for the FSP, for the wet and in the wet for the FSP, even we add the acid medium, so they are nothing different, not much different, even. So that's why we didn't continue acid, not much different. It obtain the higher, mostly of the protein still remain. We believe is a protein still remain. So this is the HSB improvement. Let me see. Okay, HSB improvement or enhancement. You see, just now I mentioned that at tolerance fraction at 300 degrees C, HSB are improved 45%, right now 1.45. But this one can be achieved by using the wet tolerance with sulfuric acid at 0.05 and only with the reaction time 10 minutes, if I'm not mistaken, this one just 10 minutes at 160 degrees C. You can achieve with the almost similar result by using the wet functions. Yeah, that's the thing. So this is a comparison. Similarly, for the SSP, they are not much impact, not much improvement as well. This one. But the result will have the similar result, which means what? This one is an element. And which means what? The wet correction with the microwave assisted wet correction able to achieve whatever the dry correction that can be achieved at 300 degrees C for 60 minutes, 45 to 60 minutes. This one with the microwave assisted wet correction, it can be achieved by only 10 minutes at relatively low temperature, which is 160 degrees C. This is the conclusion I want to make from the experiment. So of course, this is the element analysis. We just found that the H content will be reduced. H content will be reduced. I mean, it's good for the combustion. If you want to use as a solid fuel, the H will be reduced. Of course, this is the CSNO. CSNO. Why we say the by differentiate? I mean, we just assume the balance is O. Then of course, during the process, glucose and byproduct will be produced. This one through the analysis, the glucose and also the byproduct will be produced. You see, this one we don't know. We found that the glucose is produced because the further study, the next study, we further do the further analysis on the glucose. I mean, go through the fermentation can produce the bioethanol, the bioethanol that can produce up to 7%, which is a very good amount compared to this one. This one we don't know. Before that, the glucose will be produced at the same time. 5-HMF will be produced as well. And this one is one of the very important chemical in the chemical industry. So this is the TGA, just the normal TGA, thermal degradation of the this sample. This one is raw and water. The raw sample with the water. So we believe at the first stage, the degradation is the carbohydrate. Then the second stage is the lipid content. Then the last stage is the metal. Before that, you see, the rate is highest at the first stage, which is the carbohydrate degrade for the raw, and for the raw or water samples. Means that carbohydrate can be degraded. So that means what? That means they are still. Okay, we see the second one. The second one, we found that rate degradation is at the stage number 2. We did with the content, the liquid content. The carbohydrate degradation of carbohydrate at the after we adding this one is later one after the wet correction. Yeah. So that's why that means what is the second the wet correction. That means what? If we want to do the thermochemical conversion, we need to degrade the so the wet correction or correction very good. It's very good pre-treatment method to the second process because less the energy for the degradation is less. Raw material energy to for the carbohydrate. So what is the product? So it's one of the pre-treatment for the certain. Consider the wet correction as a pre-treatment want to target certain product. TGS, we found that this is a there are nothing from the gas that we can produce. The CO2 are significant evaporation, especially the acid solution. That means what? Is a cleaner product with less CO2 we produce. We found. Then the CH absorbent enhanced due to the high position. Yep. CH is what? CH is, if not mistaken, CH is methane gas. CH is methane. The methane gas is after the using the acid vector methane gas will be produced. This is the pathway will be so with the vector we have the acid hydrolysis glucose will be produced. Second stage of the hydrolysis, the 5 then can be converted into the fatty or to the hydrocarbons. So this is study. I have another study, continuous study. So that study, a more detailed study about the microalgae. So with this, we found HSP will be increased by 8. You want microalgae or solid product as a solid fuel. The HSP is increased by using the process for 60 minutes. While it can be the wet temperature degree C with the 0. More of the So for the at 300 degrees C, not only remove the carbohydrate product in the bio oil, where the lipid product was also eliminated. So most of the carbohydrate product in the pyrolysis oil was reduced by 0.39% after pre-treatment by the evaporation. And the activated energy for the carbohydrate was decreased already. For the microalgae pre-treated in the water or citric acid. So in this, the activated energy of the protein and lipid of the microalgae was increased. It means it become more stable. In short, the microwave assisted evaporation at low temperature is an effective pre-treatment for the microalgae. It is good to be used as a pre-treatment process, which can be scaled up in the future research. So this is what we show up. Here some summary. So yeah, the wet manufacturing process can be produced two products. This is the recommendation summary. Because the core product, because we found that the glucose is produced in the future, we can convert this sugar into the what? Ethanol. So low temperature evaporation of microalgae can effectively reduce the energy input for energy production, and also experiment of this one on kinetic beneficial for the reactor design. So if we do the, because in this study I didn't this slide, where is the kinetic? I didn't show you the kinetics because the kinetic study is one of the very beneficial for the reactor design, because we know what is the pathway that you want. Then you can design precisely with the products that you are desire. So better understanding of the biochar production using the microalgae, the third generation of the feedstock. Then this methodology can be applied with the high carbohydrate biomass. This one is showcases for the as a fundamental for the high carbohydrate biomass. In the future, you have the high carbohydrate biomass, then you can consider the production for large scale production with any minor modification. Of course, we need the modification because why? Every feedstock has a different characteristics of the current models. So this is the main depth reference we are using. Oh, this one is another one. Yeah, this is the pyrolysis kinetics. Pyrolysis kinetics. We can know what is activated temperature. Yeah, this is the TGA. TGA for the dry tolerance fraction. So similar, we get a similar result because the first peak is about the carbohydrate, Then for the double bar is the hemicellulose and cellulose, the lignin as the last one. Yep. So any questions?